Okay, so last section in chapter 4, 4.10, these are nonlinear differential equations. And I don't know how much I mentioned them before. I think I mentioned that that these are much more difficult to solve in general. And part of the problem is that the superposition principle does not work, right? So the superposition principle, if you remember, states that if y1 and y2 are both solutions to a differential equation, then you can get another solution just by adding the two solutions and some linear combination of them. So then that will end up being a solution. But that only works for linear equations. Does not work for nonlinear, right? So yes, if you have one solution, you can't always get the other one by, say, reduction of order. That may or may not work, right? So for nonlinear equations, if you have two solutions, this linear combination may or may not, usually it does not become a solution. And in fact, so let's just look at example 2 here, or rather exercise. Example 1, this is the number 2 in the textbook and the exercises. So we have the equation y times y double prime is equal to 1/2 times y prime squared. And so the combination of y times y double prime and then y prime squared means that this is a nonlinear equation. And we are told, or we are given, the two solutions. Y1 is equal to 1, right? So that's going to be a solution because, well, 1 times 0, right? Remember the derivatives are 0, is equal to 1/2 times 0 squared. So 0 times, right, 0 equals 0. So 1 clearly works. And then another solution is x squared. So the first derivative is just 2x, and the second derivative is 2. So if you take x squared times 2, you should get 1/2 times 2x squared. So the left side is just 2x squared, and the right side is 4x squared times 1/2. So 1/2 4x squared is indeed 2x squared. So, right, so that just illustrates that these two are actually solutions of this equation. However, you can check that if you add them, let's call it y3, if you add 1 plus x squared, right, so our C1 and C2 are just 1s here, that this is not a solution. And let's check. If I take y3 prime, I just get 2x. And if I take y3 double prime, I just get 2. So y3 times y3 double prime is just going to be, let's see, 1 plus x squared times 2. And, well, question mark. I mean, we know that this is not going to work, but let's see. If we take 1/2 times y3 prime squared, what do we get? We get 1/2 times 2x quantity squared, which is again just 2x squared, right? Half of 4x squared. But look, the left side is 2 plus 2x squared, and the right side is 2x squared. So if you take away the 2x squareds on both sides, you get 2 equals 0, which is ridiculous, right? So, right, so that just confirms that this is not a solution. Okay, so yeah, so the superposition principle does not work. If you have one solution, you have another solution. Getting a linear combination does not necessarily give you an additional solution. Okay, so that's the first thing. The second thing to note about nonlinear differential equations in general, as I think I've mentioned several times, is that these are typically much harder than solving linear differential equations. And there's no sort of set process. There's no the techniques that we've had for linear equations generally do not apply to nonlinear differential equations. So they tend to be more difficult to solve. In general, we know, a lot about linear differential equations. We know way too little about nonlinear differential equations. Right. However, in some very special circumstances, very special cases, we can solve some of them. And so I guess I'll do an example, or let me do an exercise from the book. So this will be, I'll call this example 2 for this section, and it's going to be exercise from section 4.10. Let's do number 4. Okay, so we want to solve the equation y double prime is equal to 1 plus y prime squared. And so it's, right, if it was just y prime without the square, that would be linear. But because it's y prime squared, that's why it's a nonlinear equation, right? So, yeah, so how do we do this? Well, right, as if you look at the examples in section 4.10, most of them tell you to do a substitution. We're going to let u be y prime. So you notice there is no y here, right? It's just y and y prime. I'm sorry, it's just y prime and y double prime, right? So this substitution should make it easy because y double prime is just u prime. So now we transform this into u prime is equal to 1 plus u squared. Okay. Now this equation is actually linear, and it's one that you've done many times already, right? So think of this as the derivative of u with respect to x. This is 1 plus u squared. So in fact, this is separable. We can divide by 1 plus u squared and multiply by dx. And this is perfectly set up for integrating. The integral of 1 over 1 plus u squared, you should know by now, is inverse tangent of u. And the integral of x is just, the integral of dx is just x, plus a constant, so I'll call that c1. So inverse tangent of u is x plus c, or x plus c1 rather. So to solve for u, just take the tangent of both sides. So u is just going to be the tangent of, and then this is important, x plus c1, right? The c1 goes inside the tangent here. You're taking the tangent of both the x and the c1. Okay, so great, we solved for u, but remember, that wasn't the original problem. We wanted to solve for y. So we just have one more step to do, one more integral. U is just y prime. Right, plus c1. Right, so this is, yep, this is dy by dx. So I think we can just do this integral directly. Y is just going to be the integral of tangent of x plus c1. So you get a little mini substitution here. You can say v is x plus c1, but the integral of tangent, well, I have to think about that for a second. I think it's the natural log of the absolute value of secant of x plus c1. And because we just did an integral, we get another constant of integration, so we get c2. So I think that should solve this equation here. Yep, natural log of absolute value. We should keep the absolute value. You never know when this is positive or negative. So I'm going to keep the absolute value in this case. C2, right? Oh, yeah, a lot of you probably remember this differently. You might remember it as negative natural log of cosine of x plus c1. Either way is fine. Right. So I think that solves this equation here. Okay, so yes, this technique of substituting u for y prime, is a very common technique, especially for nonlinear equations, or anytime you don't have, y itself in the problem. Okay. I think I'll do one more. Again, this entire section, there's not a lot of questions to ask about it, right? Like I say, these are very special cases where we can solve equations like this. So I think I'll do one more, and then we'll just move on to chapter 5. So this will be example 3, and example 3. And I think I'll take this one from the book as well. This will be number 8. So 4.10, number 8, we want to solve. So it's in parentheses y plus 1 times y double prime equals y prime squared. Okay. So, in fact, the book gives you the hint, another hint here, to use the substitution u is equal to y prime, right? And so it's the same, right? The same technique that we did in the previous example up here. However, notice that this is going to be a little trickier because we actually have y in the problem. So if we make this substitution, you might get the impression that this isn't going to work because our y then has to be the integral of u dx, and we don't want derivatives and integrals both in the problem. Okay, so this technique might not seem to work because of the presence of this y here in the equation. That wasn't in the previous one. All right. However, here's how we get around that, right? And this is also a very common technique, especially for nonlinear equations. So instead of writing u as y prime, let's write it as dy by dx. And so when we write u prime, what we mean by that is the derivative of u with respect to x, right? But right, which is also y double prime, right? So in other words, it's the second derivative of y with respect to x. But here's the key. We can reverse the chain rule. We can write this as the derivative of u with respect to y times the derivative of y with respect to x, right? So this is, this is du by dx. Yep, it's just du by dy times dy by dx. You cancel the dy's. Again, that's the chain rule, right? But notice that dy by dx is also just u itself. So this is the derivative of u with respect to y now times u. Or, doesn't matter the order, u times the derivative of y with respect, derivative of u with respect to y. Right. So du by dy. Okay, so, right, so let's see how that helps, right? So this is, remember, this is y double prime now, right? This was y double prime. So let's plug that in here, right? In the original equation, let me go back to this again. We originally had y plus 1 times y double prime is equal to y prime squared. So on the right side, we can change y prime to u. Right, so this is just u squared. On the left side, we're going to keep the y plus 1, but we're going to write y double prime as u times u prime. Well, again, u prime is not, be careful. Maybe I'll just leave it as du by dy because that's not u prime. U prime we're writing as du by dx. So the prime symbol here refers to the derivative with respect to x. So, so be careful. This du by dy, if you're not careful, you might write u prime, but that's not what this is, right? This is the derivative of u with respect to x, not the derivative of u with respect to y. Okay. So first thing to note is you can divide both sides by u here, and when you do that, you just get on the left y plus 1 times the derivative of u with respect to y is equal to u. We canceled one of the u's. And this now becomes separable, right? We can divide both sides by u, and we get du divided by u. It's a funny looking u. Let me try that one more time. Du over u. And on the right side, we get dy over y plus 1. Oops, dy over y plus 1. So perfectly separable, right? And when we integrate both sides, we just get natural log absolute value of u is equal to natural log of absolute value of y plus 1 plus your c, I'll call it c0 for now, your constant of integration. Right, and then to solve for u, you just exponentiate both sides. Right, so when you exponentiate both sides, you just get u. Again, we can drop the absolute value. You get u is equal to, well, e to the natural log of y plus 1 is going to be just y plus 1, right? And then, so e to the natural log of y plus 1 plus c0, you just get e to the c0 here, but e to the c0 is just some other constant. So I'll call that c1, which is just e to the c0. Okay? So, okay, so far, again, we're not done because we want to solve for y, but just as before, remember u is just y prime, and in this case y prime refers to the derivative of y with respect to x. Oops, c1 times y plus 1, right? So we have one more integral to do, and this is also separable. So let me scroll down a bit. Oops, I'm running out of space here. Let me scroll down. So this is going to be dy over y plus 1 is equal to c1 times dx. And you do one more integral. You're going to get natural log of absolute value of y plus 1 is equal to c1 times x. Okay, so far. Oh, plus another constant, so c2 in this case. Right, and now you just exponentiate both sides again. So you're going to get y plus 1 is equal to e to the c1x plus c2, which you can just call, right, e to the c2 is just, say, c3, e to the c1x, and then just subtract 1 from both sides. So I don't know if I can squeeze that in here, right? So this is y equals c3 e to the c1x, oh, let's just call it c2, minus 1. Okay, so let's go back to the original equation here. This is the equation we were trying to solve, and this, let me write it over here so we can see that better, should be the solution. So y as a function of x is just c2 e to the c1x minus 1. Sorry about that. Right, so yeah, this one's a little more complicated simply because if you have both y, or if you have all of y prime, and y double prime, you still use this substitution, u is y prime. However, to avoid having both integrals and derivatives in the same equation, you got to do this little reverse the chain rule technique and get a differential equation with u and y, right? Integrate that, and then integrate one more time to get y as a function of x. So I hope that helps. Again, forgive the relabeling C3 as C2 here, so a different C2 here. In fact, this should have been my C3 or whatever, say C4, and then yeah, so e to the c4 is my c2 here, c2. All right, okay, So I hope that helps. And so this is as far as I think I want to take the topic of nonlinear differential equations. It's maybe try a couple problems in the homework and that's about it. It's really not something we want to dwell on in this course. I mean, you can take whole courses in nonlinear differential equations, especially in applied to dynamical systems where you get chaos. But yeah, not for a first course here.